Now we are about to deal with induced EMF equation in induction or synchronous machine. The same equation appear in synchronous and induction machine. There is something different, which is KWE. That is the winding factor of armature. In fact, you remember such an equation from transformer. 4.44 times maximum flux times frequency and number of turns in the winding. That was the induced equation of one of the transformer winding. But in case you are having a distributed winding, such as in induction motor, we have already completed, there is a new factor, which is winding factor. And again, we are in the same topic. In synchronous machine, in the beginning of the course, I have mentioned that the armature winding, I mean stator winding, is identical to what it was in induction machine. So it is identical, the equation is also identical, but here's a factor, the same factor in induction machine as well as synchronous machine, the same factor, but let me cover it in a more clear way to understand it more clearly. Let's talk about windings. In fact, there are lots of winding types. It takes too much time to cover all the windings, but I just give some information about the windings, how they look like, how can you calculate, how can you understand windings easily. Okay, first of all, that is a conductor. And here are two conductors connected by end connections, producing a turn. That is one turn. This side of the turn is called as end connection. And those are the active conductors. Active EMF inducing conductors. Those conductors are in the iron core. So those parts will induce electromotive force or force, and those two are connected together to get a one turn. Those are end connections. And then you have multiple turns. Let's say here's the end turn. 1, 2, 3, 4, 5, blah, blah, blah, blah, blah, and end turns. That is called as coil. That is one conductor. Definition. That is one turn. That is a coil. One coil, a coil. Having n turns, there would be some other type of coils. For example, coil would be like this, as a representation, of course. Here is n turn, for example, and then here is another subcoil carrying some number of turns again. That is the second subcoil. Let me show you. Here's the third subcoil. All those are in the same size. It is difficult to draw here. So that is one coil having 3 subcoils. A few minutes later, I will make a definition, and here is Q, which is number of subcoils in a coil, is 3 here. Here is 3 subcoils. Subcoils also can be done like this. Some conductors connected to each other. We are having N turns, for example, here, and then here's another subcoil having some turns, and then another subcoil having some coils, number of turns. That is the final end of the coil. Again, that is one coil having 3 subcoils. Again, those are coil sides. One coil has 2 coil sides. That is a lap coil, lap coil. That is lap, burada üst üste binişen kiremit görünümlü bir yapı oluşturacağı için lap ismi veriliyor. That is concentric coil. Konsantrik eş merkezli demek. Bunun merkezi burada bak. Aynı merkezin etrafında genişleyen concentric coil deniyor. Şimdi here I have shown you some coil types. In the machine there will be much more coils connected to each other, and generally conductors will carry some current, whether they are inducing or applied. Sometimes they induce EMF, and that induced electric power will be supplied to a load, and there's a current. Here you see 2 current changes, one upward, one downward. That means, let me say A prime. The phase difference between A and A prime is 180 degrees because the currents are reversing right now. Okay. Here's another case. Currents. Here are current groups. As you see, current groups. Again, here are 2 current groups. That means such a machine or such a coil will generate one pair of poles. Briefly, one coil can generate one pair of poles. Here you see 2 current groups, and apply some current upward, downward, and then here upward, downward, and then here upward, downward. Here are 2 current groups constructing one pair of pole or 2 poles. Any coil can produce 2 poles or one pair of pole. What about winding? Some coils will be connected to each other to construct a large circuitry called as winding. 3 coils construct a winding. 4 coils, multiple coils. Winding means there are lots of coils. Generally, they are connected in series to increase and they connected to each other properly to make much more poles. Here in this example, machine can carry 6 poles or 3 pair of poles. Those are the coils. Okay. Let's give an example. Draw a winding diagram for a 24 slots 3-phase AC winding, having 2 pair of poles. That is the question. Draw a winding diagram. How to wind the machine. Let's sketch it. And here you see a 24 slots machine. Okay, let me show you stator slotted sheet. Here you see some stator. There are some slots, you see, and in the slot there are some coils or windings located. Here you see a lap winding. Looks like shingles. Kiremitler gibi. That is the stator sheet. That is the stator. Let me call windings. Perhaps here are some windings. Will be seen. Yes, there are, but it is not clear. Here's one. That is lap winding. That is lap winding you see on the right. Lap winding on the right one. This guy on the lap winding. And then let me show you a concentric winding. Perhaps I can. Yes, this guy concentric winding. Perhaps there will be a better view. Yes, this is also concentric, but it is difficult to distinguish for you. Again, it is not very clear, but here are two. Q is 2 here. One of the coil starts from here and possibly enters here. The other one comes up from here and passes to here. Looks like this. Take care. 1, 2 and 2 prime, 1 prime. A, B, B prime, A prime. That is concentric, eş eksenli. Okay, let's calculate the winding first. What we understand. and make some definitions. Number of slots in stator or armature is equal to 24 slots. Okay. Number of poles. There are two pair of poles, so number of poles are 4. And then phase number, 3 phase. Okay, concentric winding. I'm sorry. Draw a winding diagram and use lap type winding. There will be some other type of windings. Let me show you. Lap 3-phase, excuse me, 3-phase lap windings. Here you see some. That is the 3 lap winding. Q is 2 here. That is the coil having 2 subcoils, blue one. And then here's something not symmetrical. I don't like it. Yes, that is the lap winding. In fact, you can watch the drawing in YouTube here in English possibly. And let me show you another one that is also good, how it look like. Q is you see Q is 2. Okay, that's a good image. That's a good image. Salient pole synchronous machine. You see salient poles in rotor, and then here's the stator. Okay, you see again a 4-pole blah blah AC lap winding. And let me show you another 3-phase AC concentric winding. You see a concentric winding. For example, let's talk about blue one. Here blue coil has 3 subcoils. 1, 2, 3, 3 prime, 2 prime, 1 prime. Return of the 1 to 3. Again, there's another color chosen for the second phase or third phase. There is another color chosen for the next phase. That shape looks like lap winding, belongs to lap winding. Perhaps you will see some more. That is also concentric winding, having 6 subcoils, 1, 2, 3, 4, 5, 6, and their returns. As you see, current change of current direction will define the number of poles. From here to here, 1 pole, 2nd pole, 3rd pole, 4 pole. In fact, here's a little bit trick. You can in fact generate or produce 8 poles by changing the connection of windings. Let me show you. For example, I will clear this page, or let me open another blank page here. For example, show you a coil having 3 subcoils, that is only a diagram representing the location of coil ends. One coil, first, second coil end, third coil end. Those are the representation. Here's another 3 subcoils. Here is another 3 subcoils. And let me show you it. Here's another 3 subcoils. And then, if you connect those coils like this in series, let's say U and X, and apply some current, upward, up, up, down, down, down, up, up, up, down, down, down, up, up, up, down, down, down. Here you see 1, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th. 8 poles right now. But you can also make some change. For example, I will delete this page. Oh, okay. I have deleted. Here were 8 poles. Okay, and then here's the second coil having sub 3 coils. Here's the third one having 3 subcoils. Here's another coil having 3 subcoils. In this case, let me make a trick, connection trick. Instead of connecting here, I connect here, and then here, and then here, and then out. U and X. Apply current. In, up, up, down, down, down, down, up, up, up, down, down, down, and then up, up, up, down, down, down, up, up, up, down, down, down. And let's take care how many times current has a change. From here to here, you have seen only one direction of current. From here to here, the second pole. From here to here, the third pole. From here to here is the fourth pole. Now you see 4 poles. It depends the connections, in fact, but sometimes the most common case is the first one. You should remember, to produce 4 poles, you need 2 coils at least. Otherwise, you cannot manage. 2 coils, 1 coil, another coil, connect, up, down, up, down. You have seen 4 current chains producing 4 poles. Okay, each coil produce 1 pair of pole at least. But there are some other arrangements like this, making different number of poles. It is possible, but it is not general. Okay, I delete this guy and then continue our topic. 24 slots. Okay, our machine has slotted construction. Here you see some slots. It is circular machine. Stator is circular, but let me draw the stator in planar, düzlemsel form. Okay. Here you see one. Let me change color. Here are 1, 2, 3rd, 4th, 5th slot, 6th slot, 7th, 8th, 9th, 10th, 11th, 19th, 28th, and 24th, the final slot. After 24th, since machine is circular, you observe the first one. Before the first one, you will observe 21st one. Because machine is circular. Let's say 1, 2, 3, 4, blah, blah, 24. After 24, again, it repeats 1, 2, 3. Or in left progress, 1, 24, 23, blah, blah, blah. Okay, that is the planar representation. In this representation, there must be 4 poles. Okay, each pole has number of tau p number of slots. Okay, let me show you. I mean, machine has 24 slots, and then since machine can carry 4 poles, that is the tau p, the pitch of the or length of the pole, pitch or length. That is 6 slots per pole. Okay, ladies and gentlemen, let me show you. Here is 6th pole. First 6th pole belongs to, let's say, M pole. I'm not sure. The second one will belong to S pole, for example. And then here is the 3rd pole location and the 4th pole location. Those are the fair share of poles. Those are the poles, possibly poles. I am making a plan. And then each pole will be generated by 3 phases. Each pole will be generated by 3 phases. Number of phases. Number of phases. I mean 6 slot per pole over per phase. That is called as Q. Aha, I know this guy. That is Q. Number of subcoils in a coil. Q is number of subcoils in a coil. Okay, here's another explanation. 6 over 3 makes 2 slots per pole per phase. Per pole per phase. Aha. Q also can be defined as number of poles under number of slots. Number of slots under one pole per phase. Bir kutup altında bir faza düşen oluk sayısı olarak da söylenir. Aynı zamanda bu bir bobindeki yan ufak bobincik sayısıdır. Subcoil sayısıdır. Her şeyi yaptık gibi aslında. Bir iki şey daha yapalım. Okay, let's make some more additional calculations. What is the geometrical angle between the adjacent slots? Okay, the machine is a whole circuit having 360 degrees over 24 slots. 24 slots. Number of slots, that is gamma geometrical, can be written as 15 degrees in geometrical angle. In geometrical angle. Remember, electrical angles is equal to number of pole pair times geometrical angle. Machine has 4 poles. Here in the example it is given 4 poles or 2 pair of poles. So 2 times 15 makes 30 degrees electrical displacement or phase difference between adjacent EMFs. I mean, assume that here's a conductor, here's another, let's say A and A prime, and then the phase difference between A and A prime is equal to gamma electrical. That is the phase displacement between adjacent slots in electrical manner. Okay, I clean this and then I make a proper arrangement. In some books it is also called as number of colors. In some books. Okay, what does it mean? It means choose 3 different colors. For example, I choose red one. Since Q is 2, number of colors or subcoils are 2, I write 2 and then another 2, another 2, and then change color for the second phase. Those are the second phase coils. Those are coil sides. And then choose the third color, third phase coils. Here you see I have been planning a winding. Winding will look like this. Those are the active coil sides. And those coil sides will be connected in some manner. In the question, it is written as lap winding. Connect them as if it look like shingle or chain loops. Okay, let me show you. From here to here, here to here, from here to here, and here to here. Let me say U, that is the first terminal, and that is the end of the coil. In fact, the coil is wound around here. Here would be n number of turns, and then here's a jumper, and then here's another coil. That is the end of the first coil, and then let me draw it again, and then here's connection between the coils to produce a winding. And then here's another one. This is just a representation. I will clean here. I said I enter here and then turn n times, for example, and then jump to the second subcoil and turn n times, and then pass to the second coil. But let me clean here for a better picture. That is just a diagram, not all the circuit. That is just a diagram showing how they connected to each other. Okay, that's the end of the first phase, U and X. For example, apply some current, up, up, down, down, up, up, down, down. What you see here, you see what you have planned. The first pole, the second pole, third pole, and fourth pole. Okay, let's continue with the second phase. You remember, we in old terminology, UX, VY, and WZ. That is the old terminology, or newer one, U1, U2, V1, V2, W1, and W2. That is the new terminology. I've shown here is the older one. Okay, let's find out where the second phase is. Take care where the second phase is. Tata, electrical angle will help you. There must be a 120 degrees phase displacement between phases, phase coils, phase entrances, electrically. Okay, let me count up. 30, 60, 30, 60, 90, 120. Ta-ta! 120. That is the second phase, gentlemen. V, not here. Second phase starts from here. Let me show you again. That is the electrical displacement between adjacent coils, which is 30 degrees, and then I count up. 30, 60, 90, 120. Aha, that is the terminal point of second phase, V. Now, connect, jump to the second coil, connect, jump to subcoil, and terminate the coil. That is the termination. Apply the second phase current, up, down, jump to the second coil, up, down, and final down. Here you see again everything looks like what we have done, what we have planned in the beginning. Let's find out the third phase, where to enter. Start from the second phase, from here. 30, 60, 90, 120. Gentlemen, 120. W. Aha. Jump up. Connect. Jump to the second coil. Tat. Hocam, there is no return. Tata. Return is here. Let's say 1 and 1 prime. 1, let's say 1 to 1. And then come back here. Let's say 2. Here's 2. Because machine is cyclic. And then here's 3. entering here, and then finally that is the end. Looks like end. Okay, that is the Z. You have connected the third coil, and there is one thing to remember. In three phase, remember, red color first. That is the, let's say, first phase, R phase. Green one, maybe blue one is the second phase. 120 degrees later. That is the blue one. And the final one is the green one. You remember, in a symmetrical three-phase circuit, summation of the currents are 0. So, if there are two entering currents here, let's say here, red and blue ones are positive, so the green one must be negative. Aha, here is outgoing current, gentlemen. Those are entering, the third one is outgoing. It is just the reverse because of three-phase property. If two of them are positive, the third one is negative in three-phase currents. So just we make a snapshot. So that is the outgoing, incoming, outgoing, incoming, and incoming. Ladies and gentlemen, as you have seen from the figure, that here are 4 current groups producing 4 poles. In fact, it will be discussed. Sometimes magnetic axis, we say magnetic axis is between the current changes. I will show. Sometimes we say under these coil sides there is a pole. There must be pole. Let me show you here. Let's take care of this guy. Assume that here's a stator having only one pair of some pair of slots belonging the R phase. Okay, and then apply right hand screw rule. Let's say those are cross, those are dot. Right hand screw rule. That is the magnetic axis of these coils. Magnetic axis of these coils. But sometime I say, let's consider this guy, the magnetic axis just between the current changes. For example, here is the current, here is the return, so magnetic axis will be somewhere here. In brief, magnetic axis, in fact, magnetic axis of the coil, one is here, the other is here, between the current changes. The other is here, and the other is here. Magnetic axis of those are the magnetic axis of those coils. But someone can also say that. Here are 2 coils, subcoils, to construct one coil, and then, hocam, you said in the armature reaction theory, here would be such a salient pole, for example, and when you rotate this guy, magnetic axis D is here, that is the position of where electromotive force has maximum value. You said. Yes. But I mean the magnetic axis of this guy somewhere here, as I show in the upper picture. But the magnetic axis of the rotor is this. So someone can also say those coils are under the M pole of rotor. Those coils are under the S pole of the rotor. Those coil sides must be under the M pole or S pole. It doesn't matter. I don't know which pole, M pole or S pole. And those are in a different, under the different pole. That is how we generate poles. That is how we construct an AC winding. Now, ladies and gentlemen, if you apply three-phase electric current to such a coil, we will produce rotating magnetic field. We have explained in induction machine theory. Please, you can find the video. I have uploaded the system in the electric machinery course 1. You can easily find out somewhere here. Okay, that is the three-phase AC windings. Let me summarize, and in fact it is just a summary, just a sketch how it looked like. In fact, there are lots of books covering hundreds of pages because there are lots of different winding types. Here I mention only lap winding. I have mentioned a little bit concentric winding, but it doesn't matter. What matters is the pole construction, how they look like, is it very difficult or not, and the electrical displacements, and why we use such a winding arrangement, and what are the structure of a winding. It starts from a conductor and then it produces a winding. Here is the winding. Generally there are two types of AC windings. One is lap windings, look like shingles, kiremitler, or chain. And then the second type is concentric winding. You are not responsible of those topics, but again I emphasize, I lecture this topic to understand this term, which is winding factor, better, because you should know some about electrical angles, and you should know Q, which is the number of slots under per pole per phase, number of slots under one pole and one phase. Let's talk about winding factor. Which is represented by KW. That is winding factor. Okay, in fact there are two major properties of AC windings in rotating machines. Two different properties. One is, as you see from the picture, windings in a rotating machine is distributed along the slots in the stator and connected in some manner, generally connected in series to construct a winding. Of course, we generally use three-phase windings. In such a picture, there are properly arranged serial connected three-phase windings. The main property is they are distributed. For example, if you construct a winding in only one pair of slots, first slot and second slot, for example, and here's the winding carrying those that is the winding installed in those slots, that is the concentrated winding, let's say cross and dot. Here you see first side and second side of the coil, that is concentrated winding or a single coil. But today we generally use distributed windings. Here is the stator. There are lots of slots carrying coil sides. Let's say here are number of Q times coil sides carrying one coil of, for example, one phase. Let's say one phase only carry one coil, such a distributed coil, for example like this, A, B, C, A prime, B prime, C prime. I mean A prime, B prime, C prime. Here you see such an arrangement. That is the one coil having three subcoils, one coil having three subcoils. I mean Q, which is number of slots under per pole per phase, is 3 here in this example. You see, today we use distributed winding. What will be different between, what is the difference between those two type of coils or construction? Okay, let me show you. Here is, let's say, N coil, N turns totally. Here are N turns totally. So one subcoil carry N over 3 turns, since here are three subcoils. Now, ladies and gentlemen, we have know about electrical phase displacement between the EMFs in the adjacent slots. Those are the EMF in the between adjacent slots. So in the first one, those guys and those guys will be connected in series. Let's substitute a pole here, let's say N and S, and rotate that salient pole in clockwise direction, and apply left hand three finger rule. That is the induced EMF's direction, that is the polarity, and that is the reverse of the polarity due to reverse magnetic pole. So those EMFs are, let's say, A and A prime, the A and A prime EMFs are at a 180 degrees phase displacement because they are just the reverse of each other. There is an 180 degrees phase displacement between those coil ends. So the induced EMF will be very good. I mean, the A and connected series with this guy, which is EA prime, making EAA prime. Okay, and now let's substitute a salient pole again here, and then rotate it in clockwise direction, and then apply left hand three finger rule. Similar induction will occur, but here in this case again let's talk about the first A prime. The side A and A prime, those are just opposite, so the induced EMFs will be like this: E A prime, and totally construct EAA prime. Okay, and then, ladies and gentlemen, take care. Houston, come on. The phase difference between those two, gamma electrical. The phase difference between those two, gamma electrical. So in this example here, you observe EAA prime, and then there is one more EBB prime, there is one more ECC prime. Finally, having such a resultant E, we have resultant E like this here in non-distributed winding, but here you see distributed winding will have a different summation. Ladies and gentlemen, vectorial summation of those sub EMFs magnitude will be smaller than the algebraic summation of individual EMFs. And that is less than unity. Here you see, let me show you algebraic summation. AA prime, ABB prime, and ACC prime. That is equivalent to in fact concentrated winding in one pair of slots. AA prime concentrated, which is not distributed winding. It is equal to algebraic summation of the EMFs. But here you see resultant EMF, ladies and gentlemen. Resultant EMF is here. Vectorial summation is here. And it is less than unity. Conclusion. if you distribute coils along slots, resultant EMF will reduce. Magnitude will be reduced or will reduce. The reduction ratio is called as distribution factor. Distribution factor. Aha. So here you see a distributed winding. So induced resultant EMF will be smaller due to distribution. The factor is defined by KD that will reduce the induced EMF. Here you see. In transformer there is no distributed winding. In transformer the equation is 4.44 times phi max, frequency and number of turns in primary or secondary. But here we have some distribution in induction machine and synchronous machine. Since we have distributed windings along stator, so there is a reduction or reduced EMF introduced by this coefficient. Called as winding factor. Okay, KD, that is introduced by KD. In fact, in general, KW. KD is the distribution factor. Since we have distributed winding along the stator, there is a parameter coming, which is KD. But there are some other parameters changing the magnitude of resultant EMF. Okay, what is the value? What is the equation? How can we calculate that reduction ratio? How can we calculate distribution factor? Okay, let's start. Assume that there are Q individual EMFs in subcoils connected series. So the first EMF, the second EMF, and third EMF. Here are Q EMF components, Q times EMF. You already know. Here you see Q is 2 in this example. Here are two individual two subcoils connected in series, or that coil is distributed under the pole. Let's say, let me define this as EQ, individual element, that is another EQ in terms of RMS value, but they are displaced by gamma electrical. Aha, here you see some phase displacement. And that is the resultant EMF. Which is the vectoral summation. And we try to find out vectoral summation over Q times EQ. Vectoral sum over algebraic sum, and that is called as K distribution. Okay, let's try to calculate it. Here is an angle, gamma E. We know gamma E. And then here, let me say, how can I manage this? Let me draw a intersecting line here. Let me make another intersecting right line. Let me make another one. All those meet at a point. All those meet at a certain point. Let's say center. All those meet at a center. The angle from here is equal to let me show you the angle that is let me show in different color. It's a bit confusing. Blue one, okay. Get closer. Okay. That is the angle. If you draw a perpendicular line, which is one is this, this line is perpendicular to this green one, and this line is perpendicular to I'm sorry, this line is perpendicular to this guy. So the angle between those two originals is equal to angle between the perpendiculars. So that is also gamma electrical. Gamma electrical. So let me show you some more. In fact, this guy is gamma electrical. In fact, that is the angle gamma electrical, and that is the angle gamma electrical. So totally here are Q times gamma electrical. Q times gamma electrical. Let me say here is R. Okay? So I can calculate this portion. This portion is R times sine R times sine gamma E over 2. That is the triangle. That is half of gamma electrical. Gamma E over 2. That is this portion. And then two of them make total this, and then that is the EQ. Let me substitute it here. KW, KD. Here you see 2R sine gamma E over 2. That is the algebraic summation. We have just calculated one. So beep, beep, beep, beep, beep, beep, beep, beep. Here is Q. So here must be Q. Okay. That is EQ. We have just calculated. And then what about this guy? Let me show you. From here, here, and here. This side is R times, that is the radius I have already mentioned, times sine the angle Q gamma E, but half of it, Q gamma E over 2, Q gamma E over 2. That is only 1/2, and here's another, so 2. That is the vectorial summation. 2R sine Q gamma E over 2. Okay, ladies and gentlemen, here in the equation you see 2R will eliminate each other. The final equation, KD, distribution factor, is sine Q gamma E over 2 over Q sine gamma E over 2. That is the distribution factor. Here are some angles, which is P times gamma geometrical. In harmonic theory or Fourier, in Fourier manner, all the angles will be enlarged by the harmonic order, nth harmonic. So this distribution factor can be expressed for the nth harmonic, that is called as space harmonics, harmonic order. Space burada uzay değil, boşluk olarak, hava aralığı boşluğu olarak geçiyor. Space harmonic order number E. So that is the equation again, sine Q gamma E over 2 over Q sinus gamma E over 2, and now all the terms, angles, must be enlarged by E. That is the harmonic order. Here is harmonic order. Okay, that is the distribution factor for the eighth harmonic, eighth space harmonic. But we don't deal with these space harmonics during electric machinery course 2, so we only deal with this. We assume that machine windings are distributed sinusoidally, there is no harmonic terms, so that is the distribution factor. In fact, there is one other major design property. One is, I have mentioned here, distributed winding. Windings are distributed along the stator. Here we explained distribution factor, and the second factor is pitch factor. Adım faktörü veya kirişlenme faktörü. Tam İngilizcesi pitch faktör, adıma tekabül ediyor. Let me explain what it is. Any winding in the stator, I have located, here's a concentric winding like this, okay, A and A prime, here A and A prime, that is called as, let me show the rotor. Here's N and S pole in the rotor and rotating at the speed of Ns, and induce electromotive force between those coil sides. If it rotates in clockwise direction, here's cross and here's dot, so polarity of EMFs will be like this, and the induced electromotive forces armature E, side E and side E prime will be summed together and make EAA prime. That is the perfect summation. EAA prime. Perfect summation. Those are 120 degrees, 180 degrees displaced by each other. Armature EMF in the site A is displaced by 180 degrees from EMF A prime. There is an electrical displacement between those two sides. So they are just reversed, as you see here. So induced total EMF will be this. Okay. Take care. What will happen? What will happen if I make a small change in the return? For example, instead of having whole pitch coil, beep beep. In fact, you know, any magnetic pole, any magnet between the reverse poles, there's 180 degrees electrical displacement between magnetic poles. That is the electrical angle, and that is called as whole pitch. Whole pitch. Tam adım. And now you see a whole pitch coil. Sometimes we say a diameter coil, because this guy is on the diameter, a diameter coil. Okay. Now, instead of having diameter coil, we made another attachment. We locate coil on a cord. That is cord. That is diameter. That is cord. Kiriş cord. You see a cord, all fractional pitch, short pitch coil. Let's say short pitch coil. Kısa adımlı bobin deniyor. Here's cross and here's dot. Here's the magnetic pole of rotor, and it is rotated in clockwise direction. Okay, here are the EMFs induced in the coil. Plus and minus, and again looks like plus and minus, but here is something different, ladies and gentlemen. Let's say A site A prime, A site beep beep, A site A prime site. What is the electrical phase displacement between the poles, between the sides? Yes, it's a bit complicated. Let me say beta. That is the angle beta. That is the angle 180 minus beta. 180 minus beta. That is a bit short pitch. Instead of 180, there is a shortness angle, chording angle. The EMF between the return path and entering path is here. So how can we make a summation? Not, ladies and gentlemen, take care. EAA prime is not a perfect sum, because they are not on the diameter, or they are not whole pitch coil. What does it mean? It means, take care, I should explain at once due to time constraint. That is the EMF on the left hand side, Houston. In fact, in case there is a whole pitch coil, it was something here, EA prime. Remember, it was here. If it is a whole pitch coil, but in short pitch coil, there is beta. So, gentlemen, the second side is a little bit displaced by beta. Okay, what is the summation? So summation is this. That is the total EMF. Again, total EMF in vectoral summation will be smaller than algebraic summation. Shorter than algebraic sum. Algebraic sum over vectoral sum. That is called as pitch factor, ladies and gentlemen. If you have a short pitch coil, induced EMF will be reduced. There will be no perfect summation due to phase differences. Okay, now let's calculate. One side, let's say E, and the other side of the coil, E prime, and then that is the summation. So that is the angle beta. Okay, and now beta. Here's a better, shorter explanation. Beta must be beta half, but okay. Let me show you. This angle is 180 minus beta. Okay, and here's a perpendicular line. So the half of it, let's say 180 minus beta over 2, which is 90 minus beta over 2, this side. So as you see, here is a beta half. Okay, and then here's hypotenuse. EA times cosine beta half, this guy, and double of it is the vectoral summation. One is cosine beta half and double of it. Okay, what is the algebraic summation? Algebraic sum is equal to double EA, as you see. One is this, the other is this, so double A. So Kp, which is vectoral summation over algebraic summation, is equal to vectoral summation double EA cosine beta half over 2EA, and then as you see, those terms eliminate each other. Kp, which is pitch factor, can be easily calculated cosine beta half. That is the short pitch angle, shortness or short pitch angle. Okay, that is the pitch factor. Those are Kd and Kp are the major parameters affecting on EMF or MMF. Because, ladies and gentlemen, we use a winding to produce electromotive force or to produce magnetic field in the beginning. But when you make energy conversion, in fact, those two come together. We always generate those two together when there is an electric energy conversion. For example, in the beginning, in a generator, you want to generate an EMF, but after there is an electrical load applied, there is an electric current, so electric current will produce MMF, as you see. Now, finally, we call winding factor in small case letters is equal to Kd times Kp. All those are less than unity, so Kw is less than unity. In fact, there are some more factors I have introduced. One is skew factor in induction machine theory, Eichlich theory, and there is another one, K chi. This is a slot opening factor, but they are very rare. This is also only used in a rotor portion or some induction machines, in squirrel cage type machines, but in synchronous machine, that is the major one, this guy. Kp is not common, but those two are again most common ones. So winding factor today we have introduced to you is equal to Kd times Kp, even if here are some other factor components. Now in synchronous machine we don't deal with skew or slot opening. In fact, in large machines there must be slot opening, but if you will be in designer in a master degree, so you deal with slot opening factor. It looks like skew factor. The formulation is a little bit different. Slot opening means if a slot is very large in comparison with the pole length. If there is a very large slot opening with respect to pole length, there will be another factor which is K chi. So, but we only deal with this guy, Kw, slot winding factor. And today I lecture to understand this equation better. I have first explained how three-phase AC windings look like, how can they will be calculated, and then what is the major design parameters affecting on a winding, and how they will be introduced in EMF or MMF. Now you see the equation. I will talk later. Okay, that's the end of today's course. I hope you will understand winding factor. In case any question, please write down. Otherwise, see you on Thursday.